Well, hello everyone. Ahoy, mateys. I am Dan Brush Chalkwood, and welcome to this afternoon's very special Monkey Island themed training session on sentiment analysis. First of all, delighted to see of all the moments in HSMA, I think seeing some wonderful pirate names popping up, waiting in the waiting room was a real highlight for me. So fantastic. So keep them coming. This afternoon we're going to be talking about sentiment analysis, and we've got some really interesting activities for you to take part in. And this is all going to gradually lead up to a big activity at the end, which you will find out about a bit more in due course. But first, we're going to talk to you about sentiment analysis and what it is, and you're going to see how we can use sentiment analysis, text classification methods in order to try and analyze our text in a slightly different way, much as we did with the Titanic data. So, what do we mean by sentiment analysis? Basically, it's a kind of text classification approach in which we're using AI-based methods to try and automatically identify. Sorry, I'm just going to go back. So it's there we go. To automatically identify the sentiment or tone of a piece of text. So we're trying to basically work out whether if we present a piece of text, whether it is positive, negative, or sometimes even neutral in tone. And just as we looked at this morning with Spacey, where it's trying to use AI methods to predict whether a word or group of words is a named entity, here we are saying, is this text positive, is it negative, etc. And as I sometimes we will also assess whether it's neutral. We won't be doing that today. My personal instinct on it is I don't know how useful that can be, because that usually just means you've got a mix of positive and negative, and I don't know how useful that is in itself for the kind of things you'll be doing. But you can do that, so just be aware, and using the same kind of approaches we'll be doing here. So really, the kind of sentiment analysis that we're going to look at this afternoon is very much like any other classification problem, just like, when we were trying to predict which passengers survived or died on the Titanic, or which stroke patients needed or could have clot-busting treatment or not. The only difference, although it is an important difference, is that we are working with text data here, which means there is extra stuff that we're going to have to do. And we touched on some of those things a little bit last week in the intro session, but we're going to explore some of those things in a bit more depth, because we're basically going to be creating a neural network this afternoon. Yes, we're back to those things, but feeding through some text data. So why are we kind of teaching you how to do this? Well, sentiment analysis itself is a type of text classification problem, even sentiment analysis as a thing is in itself quite useful. And in fact, if we think, and you may be able to think of other examples for health, social care and policing, but you could imagine using this kind of approach to automatically classify various patient or service user data positively or negatively. Patient surveys, service user surveys, that kind of thing. Analyzing social media posts, things that people are posting about your organization, to try and identify whether it's positive or negative. And again, we can combine these things with the named entity recognition stuff we were looking at this morning to try and see whether we can also identify what they're talking about positively and negatively as well. But of course, just because we're teaching you sentiment analysis here, the same principle is just a type of text classification approach. So you can follow exactly what we're doing here if the thing you're interested in is not classifying by sentiment, but classifying by your text by something else. So as I mentioned before, one of our previous HSMA projects from last year did a text classification project using the same kind of approach, but was looking to see, okay, I want to classify social media posts to see whether they are talking about illicit drug use or not. So that's a text classification problem, and it's exactly the same approach that we'll show you here. So whilst sentiment analysis itself may well be useful for what you want to do, the same approach can be used for any text classification. And exactly what we're doing here will apply directly. It's just rather than classifying into positive and negative, we'll be classifying into different different classes. The only thing to say, obviously, is that just as with any machine learning, we're going to need supervised learning, we're going to need to show some examples. And there's lots of things that we can train on for sentiment analysis, but depending on what you're trying to do, you're going to need to find either something that's out there, a labeled data set, or have your own labeled data set to be able to make predictions if you're going outside of things like sentiment analysis. Okay, so as I mentioned, we're going to, this afternoon, we're basically going to build and train a neural network. We're going to use TensorFlow, we're going to use the Keras API, so just as we did in the neural network session. And we're going to attempt to classify whether some text that we present to it is positive or negative in tone. And to do that, we're going to train our model using a large open data set which contains both positive and negative movie reviews. So we're going to try and get it used to the kind of language that people use when they talk positively about something and negatively about something. And then we're going to test our model on unseen data to see how well it performs on data that it's not been trained on. So this is the broad process that we're going to follow for our sentiment analysis. We're first going to load in our text data, and we'll split it, and this time we're going to split it properly. We're going to split it into training, validation, and test sets. So we mentioned this before, that you should use a validation set, and that should be the thing against which you check whilst you're training. And the test set should be left completely alone until you finish training, you've got your finished product, and the test set is used as your kind of final benchmark of accuracy. That's what we're going to do this afternoon. We're then going to standardize the text, and by standardizing here, we're going to basically remove all cases, so we're going to make everything lowercase, and we're going to remove punctuation. We're then going to vectorize the text. Remember from last week, we said that text vectorization basically just means turning our text data into vectors of numbers. And last week we used a bag of words to do that. This week we're going to use a different approach. Then we're going to build our neural network for a binary classification problem. It's a binary classification problem because we've got two classes, positive or negative. Then we're going to train or fit our model. Then we'll evaluate the model on a test set, and then we'll save the model for future use. So let's talk through each of these steps in turn now. And just before I sort of go into this, hopefully you've all already done this, but in order to run the code this afternoon, you're going to need to download the large movie review data. Now, I would say only, because of the nature of the exercises you were doing this afternoon, only one of you in the group needs to have this working. So don't panic if you're not, because you're going to be doing this very much as in a group for all of the activities. So don't panic if you didn't get it working for whatever reason. But if you want to follow along with this stuff, that's what you're going to need to do. You will need to remember to remove the unsup folder on soup, I suppose it should be, in the train directory. That's for data that's can be used for unsupervised learning, which we're not doing. If you leave it in, you will run into problems. Basically, your algorithm will run incredibly slowly and will have terrible performance. So do make sure you take that out. I know a few people had issues yesterday trying to extract the file, but hopefully, if you look back through the various posts, I think we managed to sort everybody's problems on that. You do need to make sure, though, that by default the file path will be looking for a folder called ACL IMDb _v1 in the same directory as your Pi files for this session. If you find that isn't the case, you either need to change the file path or you need to create a new folder called that and put the extractor folder into it. But hopefully most people should be able to get that working. I'd also say when we get on to the exercises this afternoon as well, whoever's sharing the screen, I would probably advise whoever's got a slightly faster computer, I mean, none of this is, it shouldn't be horrendous on anybody's, but you may find it best, given you're working as a group, to go with somebody who may be able to run this a little bit quicker. It might help you in some of the activities without giving too much away. Okay, so the first thing we're going to do is load in our data and split it into training, validation, and test sets. Now, the data we're using for this is this large Internet Movie Database review data. This data basically contains 50,000 movie reviews, and the way the data's split up is it's split into 25,000 training examples and 25,000 test examples, and each of those is then split half and half into positive reviews and negative reviews. So essentially you've got 12,500 positive reviews in the training set, 12,500 negative reviews in the training set, and then the same in the test set as well. If you, those of you who've had a look at the extracted files, will notice that you've got a lot of files, and the directory structure looks like this, where you've got a test folder and a train folder, and then within each of these, you've got a subfolder called neg and a subfolder called pos, and within those are the reviews, and all the reviews are stored as separate text files. The reason we've done it like that, or we haven't done it like that, that's the way the data is supplied, but it's quite a good way to do it, is because there's a really nice method in Keras that allows us to basically automatically read in and interpret text data files into training, validation, and test data, separating out into the correct classes if our data is structured in that way, so that we have a test folder and a train folder, and then within that our various classifications. Now here we've called it neg and pos for negative and positive because we're doing sentiment analysis, but you could call these anything you like, and these are essentially our classes. So if you weren't doing sentiment analysis but some other text classification, they could be called something else. And basically this text dataset from directory, a little library, method, allows us to basically load in different classes of examples, as long as we've got our folders set up like that, which is exactly what we've got here. And you can read more about that particular method at this link here. So by using this text dataset from directory method in Keras, we can load in the two classes, pos and neg, for each of our three data splits: our training set, our validation set, and our test set. Now, we've already got our data split into training data and test data, because it's already come like that, which is great. So that simplifies things. But we don't have a separate validation set. Now, you remember validation, our validation data comes off the training data. We carve a bit off the training data for our validation. And remember, validation data is data that is provided to the model during training, so it can check itself to see how well it's doing and try to adjust things. So we're going to keep the test data as it is, because that's already prepared. But we're going to carve off, in this case, we're going to carve off 20% of our training data to use as a validation set, and the other 80% will be our training set. When we do that, we're going to use a random seed to fix these random numbers in this sampling here. And we do that to make sure that we don't accidentally pick the same examples for both validation and training. And if we did that, we'd essentially be giving the model information it shouldn't have access to. So we fix it so it will randomly take 20% and then leave the other 80% will be unique. So once we've got all the data loaded in and we've got it split into training, validation, and test sets, then we're going to standardize the data. And specifically, we're going to, here by standardization, we mean we're going to make everything lowercase. Some of you got through the exercise this morning may have noticed for the name density recognition that it seemed to be performing okay, but you kind of got the feeling it was missing some things that perhaps the capitalization would have helped with. For sentiment analysis, capitalization is useless. Doesn't really tell us anything, so we typically remove capitalization for sentiment analysis. So we are deliberately doing that here. And we're also going to remove punctuation. That, again, does not help us determine sentiment. Now, just to flag up, for this example, we are going to leave in stop words. We can always explore later whether removing stop words will help us. But just to keep things simple, for this example, we are going to leave stop words in. Okay, so once we've done all that, we're then going to vectorize our text. And as I say, we talked about text vectorization last week. We said that computers can't deal with numbers at a fundamental level, and simply a neural network, which is effectively performing lots of mathematical operations on some numbers that you feed through it to get to a number at the end, also need to deal with numbers. So we have to turn our text into numbers in some meaningful way. We used a bag of words last week, which is quite simple to understand and quite simple to implement, but as we discussed, has problems because of the way it works. You get these very large, sparse matrices which are very, very inefficient, and they can sort of blow up very quickly. So it's probably not the best approach if we're doing anything like this. We're working with vast amounts of text data. So what we're going to do instead today is we're going to use a layer that Keras provides called text vectorization. This is a neural network layer. And basically we're going to use this neural network layer as on its own initially. And we're going to build it as like a one-layer neural network that's already pre-built for us and pre-trained. And what this layer does is it takes in raw batches of strings, so raw text data, and then it turns them into a tensor. Remember, we talked about tensors being the shape of things that a neural network needs. A tensor of indices that can be used in a neural network. So basically it takes in raw text as strings, and it'll come out with tensors full of numbers that represent those strings. The way it does it is it creates a vocabulary of numbers that represent words based on their frequencies. So essentially you could end up, you feed it through, and maybe the word donut, I don't know, I keep saying donut, but maybe the word donut relates to, is mapped to the number 37, for example. Okay. It would also do punctuation as well, but of course we're stripping punctuation out, so that won't apply to us. Now, we can either do that manually, creating this vocabulary, or we can use an inbuilt adapt method that it provides, and that's what we're going to be doing today. So to create the vocabulary, then what we need to do, we're going to need to provide a couple pieces of information to Keras's text vectorization layer. We're going to need to specify the maximum number of words that we want represented as numbers, which essentially will be our features. And we need to specify the sequence length for each review. So let's just talk about those two things, because these are quite important. And this is a little bit different to what you're used to with machine learning. So first of all, I said we need to specify the maximum number of words we want represented as numbers, which are our features. So essentially, our words as numbers are our features in our neural network in this example. And as ever, with any machine learning problem, the more features we have, which remember are our words here, we gain more information from which we can learn. But if we use too many, it overcomplicates the model, and that can cause problems for the learning. We also know that there's likely going to be a lot of words that are not common and are fairly unique to particular reviews, and that's not going to help us much either. We're not going to be able to learn much from that. We as the modelers need to decide how many words we want to use, how many features essentially. So we're going to start in our model by default by using the 10,000 most common words across those across the 25,000 reviews in the training set. Okay, that will include stop words, remember, because we're not taking them out at this point. So that will include stop words. But we're going to take the 10,000 most common words, and those are the ones we're going to build a vocabulary. Anything else will actually be ditched. We won't acknowledge them. So just the 10,000 most common. The other thing we need to do is we have to specify sequence length for each review. Now, as I think we've mentioned before, everything that passes through a neural network has to be the same size and shape within the same neural network. You can't have different batches with the data being different sizes. But obviously, if we're dealing with free text data, so when we were dealing with like the Titanic data, for example, stroke data, sometimes we'd have missing data, and we said, well, you're going to have to do something about that. You have to either impute it or get rid of it. If you haven't got a lot of valid values, maybe you might remove that feature. But you have to deal with it in some way. And obviously, it's fairly straightforward if you've got a table of data like that. But we're dealing with free text data. Our reviews, which are our documents in this case, each movie review is a separate document. They are unlikely to be the same length. In fact, they could vary quite significantly, and that's going to be a common problem in any natural language processing problem we look at. So, how do we get around this? Well, the way in which we do it is we decide on a sequence length, and by the sequence length we mean the number of tokens that will represent each review. Remember that our tokens will be individual words here. Now, bear in mind, those tokens that represent a review won't include all the words in the review. It'll only include the 10,000 most common words that are in our training data. So we're going to start with a sequence length of 250 tokens, okay? So what that means is that if we take a given review, let's say we've got this review. Those 250 tokens will be made up of only the 10,000 most common words across all of the training data. Now here you say, well, hang on a minute, that still could be, the review could be shorter than 250 words to start with, or could be longer than 250 words, even when we're just looking at the 10,000 most common. And you're right, of course, and that will happen. In fact, it'll happen in most cases. So what we do, any reviews that then end up longer than that, so any review where we have, we've got a length of 250, if we map so that the words in that review, we're only looking at the 10,000 most common words across our training data. If that still makes the review longer than 250 words, then we basically slice it. So we ignore anything after those 250 words. It'll be truncated. If the review is shorter, then and we've got under 250 words, once we've done all this, then they get padded out using a special token known as a pad token, which the machine knows to ignore. Okay, and typically, and I believe Keras does this, you would give a pad token a value of 0 in the vectorization. So and it does that specifically, so it has no influence because it's a dummy word. Essentially, it means nothing. It's just we're padding it out because we haven't got enough tokens in that particular review. So you'll end up if you imagine these are our words. Once we've said I only include the words in our review that are within the 10,000 most common across our training data. Let's say we've only got 4 words here in our review, but our sequence length is length 7. Then we'd have those 4 words in our vector, but we'd also have to pad it out with 3 zeros as well. This one is 8, so it's too long, so we just chop off the last one, etc., etc. It does all this for you. You don't need to do this manually, but you need to be aware what it's doing, because it will ask you these two numbers essentially, how many tokens you want in terms of in our case the most common words, and the sequence length, which is the number of tokens. So what we're going to do today in our model is we're going to create a Keras text vectorization layer that uses this the standardization function that we wrote in step 2. So the one no, actually we don't. Sorry, that's completely wrong. I'm just going to make a live adjustment to that. Sorry, I didn't spot that because I'll forget. Otherwise, create text vectorization layer. So you're watching this in action. What I should say. It also standardizes at the same time. it's because it changed this year, so that's a legacy thing. There we go. Right. Okay. Let's pretend that didn't. Oh dear. Okay. Right. Yeah. So something to flag out. You used to have to do this manually. You used to have to call a separate standardization function. You don't need to do that now. You can just pass in an argument saying how you'd like your text standardized, and it'll do it for you. So all that stuff about making the text lowercase and stripping punctuation, you just tell it that's what you want it to do, and it'll do it for you. So that's really nice and easy. We'll also pass in that we want 10,000 max features and a sequence length of 250 tokens. And also we have to tell it how we want our tokens represented. There are different options. We're just going to go with integers. So basically each word will turn into an integer number, a whole number. Then we're going to grab out the raw text data from our training set. So just the training set, without the associated labels. We're going to do this using a lambda function. I'll talk more about lambda functions in a moment. Then we're going to use this adapt method of the text vectorization layer, the one I mentioned earlier. That will then create our vocabulary that will map our words to integers, basically. It'll then create a function that will apply the text vectorization layer to our text data, and then we'll call that function to vectorize the text in all three sets, so the training, test, and validation sets, based on the vocabulary created off the training set. Now, this is really important, okay? We can't create vocabulary from the validation sets and the test sets because we're not supposed to have access to that information, okay? So we cannot create vocabulary. So what that basically means in simple terms is if you've got a word that does not appear in your training data and only appears in your validation and or your test data, there will be no numerical representation for it. So it will not train on that word because it did not come up in the training data. And we build our vocabulary based on the training data. However, that is the correct thing to do, because otherwise, if we said, well, we'll let stuff in from the validation and test data, great, your performance will go up. But of course, the whole point of doing this is then showing it on unseen data, and there will be words it hasn't seen there. So where do you stop? Okay. So the point is, you have to be very strict and make sure that you are only building the vocabulary, the mapping of words to numbers, working out what the 10,000 most common words are from the training data only. You do not touch the other ones. Once you've done that and you've created your vocabulary, so word 37 is donut, word 26 is tree, whatever, that then maps, we then apply that to the validation and test data so that it maps any words that it's seen in the training data to those numbers. Okay, hopefully that makes sense. So you're using the training data to work out how to convert words to numbers, but it'll only do it, and then we'll map those mappings to the validation and the test data sets, but we will not be able to map anything of words that are only in the validation and test sets. So I mentioned a moment ago that we're going to use a lambda function. So lambda functions, there was actually, I think in Sammy's session last week, there was a little lambda function buried in there. You will occasionally see these little things. They're quite a neat little feature of Python. Don't worry too much about them, you won't use them that much, but they are quite handy little things. Basically, all a lambda function is, it's like a little miniature disposable function. Okay, so you're used to writing a function definition, you say def, and then the name of your function, and then here are my inputs, and then I want you to do these things, and then return this. Okay. A lambda function just allows you to write that in a couple sort of keywords, but you just use it once and then you get rid of it. Okay, so it kind of says, it allows you to write in a kind of shorthand to say, okay, I'm going to give you these things, give me that back, and that's basically what we're going to be doing here. So we're going to give it two pieces of information, and so just give me back. And in fact, the thing we're going to do is say, I'm going to give you the data which contains both the text data and the labels, i.e. whether it's positive or negative. I just want you to give me about the text, and we just do that, and you'll see within a couple of words allow us to do that. As I don't worry too much about it, but when you come to look at the code, you'll then hopefully understand what that means, and I've put in the comments as well to explain that. Okay, so once we've done all that, we've got our text data ready. It's all vectorized and it's all in tensors, and we've got all our numbers and everything. Then it's ready to be fed through our neural network. So we're going to build a neural network for a binary classification problem, just as we did with the Titanic data. We've got two classes. This is a binary classification problem. And in fact, a lot of the things that you'll be doing here will be pretty familiar. You're going to build up some layers of a neural network. We'll have an input layer, we'll have an output layer, and all that kind of stuff. But the specific layers you'll be using, particularly some of them, are going to look a bit different to some of the ones that you've been used to so far. First difference you'll notice is there's going to be something called an embedding layer as one of your early layers in the neural network. An embedding layer sounds complicated. Basically, all it does is it converts any data that we've got that is categorical or discrete data, and it puts it into continuous space. So it makes categorical or discrete data continuous. Okay, and that can be quite a useful thing to do if we are working with, particularly if we've got text data where we've got lots of features. So we've just said about we're going to take 10,000 most common words. Effectively, we've got 10,000 features, therefore, in our model. So what we can do is we can map them continuously rather than discretely. So rather than having 10,000 sort of discrete columns, it maps them on a continuous scale. And that generally improves the performance of our models. It also gives us a little bit of an advantage. We're not going to be doing this here today, but you can use these kind of embedding layers also to capture semantic information. So you can embed, map words that are more similar to each other closer together. We touched on this a little bit in the ethics session where I mentioned that there are packages that allow you to do this. And then you can do mathematical functions on words like man plus crown equals king and stuff like that. So you can do these kinds of mathematical operations. Now we can either use a standard untrained embedding layer, which is what we're going to be doing in the example here, or we can use a pre-trained one that's already been trained on common words. And this goes back to what we were talking about this morning about transfer learning, because it allows us to kind of fast forward through common text, because there's going to be stuff that it's going to have seen loads of times in lots of text, or even our movie reviews. It's going to contain text that is very common. And so the advantage of doing that, having a pre-trained one, is that you're not spending time training from scratch. You are starting from a sort of more a better starting point where it's already seen common stuff, and that can help with your training. It can be quite a powerful thing to do. We're not going to do that in our code. We're going to start from scratch. So our model knows nothing at the start, so it's going to learn all these embeddings, etc. But I have put a link in the comments in the code where you can see an example of a pre-trained embedding layer, and if you wanted to use that, it has some instructions for using that as well. But as I say, we'll just keep it simple for now. We're just going to use an untrained embedding layer. So this is what our neural network is going to look like. Okay, so we're going to have an input layer first. Then we're going to have this embedding layer, which is what we just talked about, which puts discrete data into continuous space. Then we'll have a dropout layer. You remember those from the neural network session? We tend to have dropout layers after each main layer, and a dropout layer will then randomly switch off some of the connections coming in to stop the model, or try to stop the model overfitting, because it's trying to stop it getting too obsessed with part of the part of the model, or a particular aspect of it. So it randomly switches off bits of it on each epoch. Then we're going to have something called a global average pooling 1D layer, which sounds quite complex. I'm going to insist that you call the global average pooling 1D layer, which is also quite commonly used in image recognition, the squishy squashy layer, because effectively that's what it does. All it does is it reduces complex data by taking pooled averages. It essentially squashes it down. So imagine your tensor going through with lots of complex data. It squishes it down by taking pooled averages and makes that less complex. Okay, and it turns out that by doing that, you end up, again, as we've talked about before, problem of overfitting often is that we've got a model that's too complex. This is another way to simplify a model. So squishy squashy does that, okay? Then we have another dropout layer, and then we have our output layer. Okay, so we've got our words coming in as numbers here. They then get put into continuous space in the embedding layer. Then we've got a dropout layer, which will randomly switch off bits of it. Then they go through squishy squashy. Then another dropout layer, which will randomly switch off bits of squishy squashy. And then the final output layer. Okay, so that's going to be our neural network. And our output layer is going to have a single node, which will represent the output. All of the other layers, all the other hidden layers, I should say, so this one, this one, this one, and this one, are going to have 16 hidden units, so a size of 16 nodes. Once we've built up our neural network, just as we did before, it's exactly like in the neural network session, we will say, I want this layer, followed by this layer, followed by this layer. This will all look familiar to you from the neural network session. We're then going to compile the model. Remember, to compile a model, we have to specify things like what optimizer we're going to use. Remember, the optimizer in a neural network is basically the correction algorithm. It's the one that goes around and changes the weights based on who got blamed for the error. Also remember, if in doubt, use Adam. We're going to be using Adam as our optimizer today, so that's good. Loss function, remember the loss function is the function of how we calculate our error, how wrong we are. You'll also remember that we said we tend to use binary cross-entropy loss as our loss function when we've got a classification problem with two classifications. That's what we used for the Titanic data. That's what we're using here as well. We've got a binary classification problem. So Adam and binary cross-entropy, exactly the same as we used before. And we also specify the metrics for success. This is how it's going to compare itself as it's training against the validation set. We're just going to use accuracy, but you can so it'll look at its accuracy and then try to monitor that and try to improve it. But of course, you can put in different metrics as well. But we'll keep it at accuracy because the principle's the same and it simplifies it. Once we've built the model, we then train it or fit the model. And we do that exactly the same as for any other neural network. We're going to train it for 20 epochs. Remember, an epoch is just one pass of all batches of our data through our network. So we carve up our data into batches, because we don't shove it all through at once. We carve it up into batches, shove each batch through, and once we've shoved each batch of our data so that all of our data's gone through once, that's one epoch. And then we move on and we do it all again. So we're going to have 20 of those epochs. If we find that our model is overfitting, which you probably will, most do initially, we can also use an early stopping callback. Remember, we talked about those in the neural network session. We said this is an easy way to use a callback where we say, keep an eye on your own training. And if you find that you are not improving on the validation set by enough, then stop, because you're probably starting to overfit. You'll see an example of that in the code. By default, it'll be switched off, but the code will show you how to very easily switch it back on, and so you can try it with early stopping. We're then going to evaluate our model on our test set. Again, this is all very similar to what you've done before. So we've looked at the training data. It's improved itself via the validation set. We'll then show it the unseen test data. Now, this is genuinely unseen this time. When we looked at the neural network session, we were cheating, really, by using the validation set as the test set. That's not what you should do. Here, we're going to show it data that it has not seen before. And we're going to look at both accuracy, which you want to be high, and loss, which is the error, which you want to be low. Now, then, once we've finished fitting our model and we're happy with it, we're then going to export our model. However, we're going to do something a little bit clever to this. So I'm just going to explain this because this can be a little bit difficult to get your head around, but hopefully this will make sense, okay? This is our trained model, okay? This is the one we're training. We said we chuck in our words as numbers into our input layer. They then get put in continuous space. Then we have a dropout layer, squishy, squashy, dropout, output, okay? We're going to take that model once it's trained. This is the one we're fitting. Once it's finished training, and we're happy with it, we're then going to bolt on to the start of that model that text vectorization layer, remember that one layer neural network we created earlier where we can chuck in raw text and out the other side pops vectors of numbers with, that represent our words? We're going to bolt that on at the start, and then at the end, we're going to bolt on a sigmoid activation layer so that we can interpret the final output as a likelihood of it being positive or negative. If it's nearer to 1, it'll be positive, nearer to 0, negative, etc. That means by doing that, we can chuck into this model raw text, and it'll then go through the vectorization layer first. It'll get turned into vectors and numbers, which then in turn will go through our trained model. It'll get shunted through, continuous space, drop out, squishy squashy, all that, come out with a number. That number then gets fed into a sigmoid function, and it says, ta-da, it's 0.8. And then we interpret that as being positive or negative, likely positive. So this basically allows us to essentially create a sort of deployed model that we could then effectively give to somebody else. We could say, okay, you can just give it some text, and out the other side will pop a number, which will be the confidence of whether it's positive or negative. Okay, and the reason we do it after, this is the bit we need to train. We don't want that there at the start because we don't need to train the vectorization layer. This is a pre-trained layer that Keras supplies. So we train the model, then bolt on these bits once we've got the fully trained model. We initially in the code, you'll see you don't do that initially when you first build the model. We take this as a single layer and we write this function that kind of shunts the stuff through that single layer, that vectorization layer. But once you've trained your model, you don't need to do that. You can just use the model complete as it is. Okay, so I appreciate there's a lot of information to take in. Let us summarize. First of all, we're going to load up our data, which is nicely in these split into these directories. We're going to split it up into training, validation, and test sets. We're then going to pre-process the data to remove things that won't help us. So we're going to get rid of capital letters and punctuation. We're going to then turn the most common text into numbers in vectors and make all the reviews the same length. We're then going to build a neural network with a layer to make our data continuous, as well as a squishy squashy layer in the middle. Then we're going to train the model. Then we're going to test it on the test set. And then once we're happy with it, we're going to save a version of our trained model, and we're going to bolt on the start that vectorization layer so we can just chuck it for raw text. And then we'll bolt on the end a sigmoid activation layer, which will output a number between 0 and 1. And we can say the closer it is to 1, the more likely it is to be positive. Sammy, any questions about any of that stuff?
No, I think we're good. The main thing was there was one query about capitals and punctuation and whether there is a chance that could potentially help with sentiment analysis. So kind of, almost inverted quotation marks around words, or, capitalizing for emphasis.
Yeah, I mean, you're right, it could. And so you might want to try not doing that. And in fact, you have the option to do that. In fact, if you depending on the data you're using, you may provide. So if you're looking at social media data, you might even want to look at things like emojis, because emojis can help you capture sentiment as well. In fact, I seem to remember that Mike Hill, who did for HSMA3, who did the police sentiment analysis thing using Twitter data, I'm pretty sure he did that and found actually it was quite useful. And found, in fact, he was starting to dive into the use of emojis to try and indicate likely sarcasm, which was quite interesting. But yeah, so depending on the data, you might want to try. General rule of thumb is you probably strip it out, but depending on what you've got, you might, and particularly the more informal your data, if you've got people will likely write differently on a social media post, for example, to a patient survey on a form or something. So take that into account. But yeah, absolutely, maybe worth exploring that.
Fabulous. And the only other one that I think was probably recovered in the summary, but just to highlight as well, someone asked just to confirm that a token here is a word rather than a character.
Yes, that's right. Yeah, so we're tokenizing by word. So individual tokens are words. They would also be punctuation if we'd left them in, but we're not. So punctuation won't exist in our data on this one.
I think that's
Cool.
everything.
Excellent. Okay, in which case we should move on to part two. Oh, the sound cut out. That's annoying. Did that cut out for you as well?
Good for me, unfortunately. Yep.
Yeah. Yeah. Okay. Well, let's just try once more. Hang on. I mean, that's better. I put that in for a reason. Okay. Right. So exercise one, the code we are now moving on to. So you're going to first of all take a 10-minute break. You'll be delighted to hear. So till 2:30. You're then going to work in your groups for 1 hour. And basically, in your groups, one of you, I would recommend the person that's got the not the slowest PC, probably. Don't panic too much, but if you've got somebody who's got something a little bit faster, get them to do it. Open up the file sa_1.py. What I want you to first of all do as a group, work your way through the code. There's lots of comments in there. Read through everything and make sure everybody is understanding how all these bits of code are working. So it's basically going to follow the steps that I just explained there. Once you're happy, I want you to then run the code. Now you're going to need to use the NLP_SA environment that we supplied to do that, and watch your resultant loss and accuracy of the trained model on your test set. You may want to note how quickly the model runs on your computer, because that might allow you to decide what you're going to do next. As a benchmark on mine, it takes about 4 seconds per epoch, and that's just running off the CPU. So I've not tried it on the GPU. It's probably going to take longer on your machine, but that'll give you an idea. So if it's taking 3 minutes per epoch, you might want to rethink how you go about this. Once you've run the model once, you'll get your kind of baseline scores on accuracy on your training, validation, and test sets, and it'll spit out the test set accuracy and the test set loss. You're then going to play around with the model, take a copy of it first, so you can always go back to it, and try changing some aspects of the model to see if you can improve the performance that you're getting on the test set. So here's some suggestions of things you could try. You could try changing the number of training epochs, particularly if you think there's overfitting or underfitting. You could do that either manually, or you could use the early stop and callback. Again, I've put in the code for the callback in there and explained how to use that, so you can do that. You could try increasing or decreasing the X most common words. We're using 10,000 by default. Is that too many or not enough? Try increasing or decreasing the sequence length in tokens of each review, which, as I say, we're going to start with 250, but maybe that's not the right size. Try changing the batch size. Be careful about going too big with batch sizes, because you can cripple your computer very quickly if you're not careful. Try changing the dropout rate. I think it's 20% by default. Try changing that. 20% to 50% is usually a good a dropout rate for neural networks. Try changing the number of hidden nodes, the number of neurons per layer. We've got it by default at 16. Try changing the layers in the network. If you're feeling ambitious, try putting in another layer. Try taking out a layer. See what happens. Try changing the proportion of the training set that we're carving off as the validation set. At the moment, it's a 20% split for the validation data, 80% for the training. Try changing that. I want you to try all these different things, and the code will automatically save the model each time you run it. You can change the file name if you want to save, and you'll see in the code where you've got the file name. If you want to save different versions of your model, then you can do that. And I'd advise you might want to consider doing that. Okay, so that you can always just load back up, and we'll see after the exercise how you do that. The best model. I'm just saying that might be helpful for the next bit. Don't know, might be. So bear that in mind. Okay, right. I will stop sharing. I'll open up the breakout rooms. Go and have a break for a bit, and then you'll have until 3:30. And we'll come back and we'll look at the next bit as we move towards what this is all building towards. Okay, right, let me stop sharing. Hi everyone, welcome back. So, you've all had a chance to have a look at your code, and my key takeaway is that Annika in Agnes has a far better computer than me. I can't believe I got our university to spend £5,000 on this PC, and I'm being outperformed. So Annika was actually running epochs in 2 seconds. 2 seconds. That's twice the speed of mine. Insane speed. Using a Mac. So these new M1 and M2 and M3 chips in the Macs, I'd heard were exceptionally good for machine learning. Turns out they are very good. So I need to turn on my GPU or get to the university to buy me a second computer. I think one of those things needs to happen. Okay, so hopefully you've had a bit of an explore of the model, and I see you've been all playing around trying to eke out a bit more performance out of it. So hopefully you're taking notes, and you've taken got a copy of the best version of the file, because you're going to need that shortly. But before we get into that, I'm just going to. Some of you may have looked at this already, but I'm just going to demonstrate this to you for those who haven't. So we've also got, because we've saved a copy of our model. Basically, the advantage of doing that is that we can then reload that model and use it at any point. We'd have to retrain it every time, and that's a tremendously useful thing to do. So I'm just going to bring up sa2.py, which shows you how to do that, and shows you then an example of applying it on some text. So at the top, we have to import the same, well, not the same things, but a couple of the things from TensorFlow that we will need in order to be able to get to load in the model and use it. So that's TensorFlow and Keras. Then I'm going to specify my file name, which if you've changed it in any way, obviously you'd need to change that file name if you want to load in a different one. But this is the default file name that SA1 will save it as. And then we load in the train model very easily just by calling keras.models.loadModel and pass in the file name. That will then be stored. Our trained model will be stored in trained SA model, and we can then play with it exactly as though we had just trained it. So here I'm going to set a little threshold of 0.5. I've just created a list of 2 reviews here. One is a review of Tenet, which is very, very positive, and the other is very negative. Now, annoyingly, if you're using Windows, because Windows is rubbish for data science, as we all know, you then have to do this line of code. It'll always be this line of code. If you're not using Windows, it won't hurt to have it in here. You just don't need to do it, but you have to if you're on Windows. Basically, what it does, it has to convert this list of text into a tensor first. Unix operating systems do this for you. Windows does not. So you have to do it manually. It converts it into a tensor shape. Then what I'm going to do is call the predict method of our trained model, the one we've loaded back up, just as if we had just trained the model, and I'm going to pass in the tensor, which is this list converted to a tensor, and then it'll basically just go through a little loop, and it'll check the output that comes out at the end, the number, and if it's over the threshold, which I've set as 0.5, it'll say it's positive. Otherwise, it'll say it's negative. And the great thing is we can do this. We can just pass in text, albeit with this little extra step if we're on Windows, to convert it into a tensor, because we've saved our model, our trained model, with this bolted on layer at the start, which vectorizes our text. So that allows us then to do that. So if I just run this very quickly, and this will run very quickly because we haven't got to train it in any way, and there is no module named TensorFlow because I'm in the wrong environment. So let me do that again. Here we go, it should work this time. First, let me wait for it to connect. There we go. So it's predicted this glowing positive review, very confident positive, very near 1, predictably positive. And the review, the movie was a load of rubbish, very confident negative. So this is just based on the stock model. So I haven't made any adjustments to mine. This is just based on the stock model, the one that the original code that I gave you. Okay, so my thing. Okay, this is all well and good, Dan, but where is this all leading? Let me just because I don't think I shared this right. 2 seconds. Oops. Nope. Yeah, there we go. Right, so you've got your models. Hopefully you've tweaked them a little bit, maybe eked out a bit more performance. Don't worry if you've still got a few little bits to do. There will be a little bit of time if you want to make any fine tuning adjustments shortly. But you are about to use your models for the next step in today's activity. What is the next step? Let's find out. Okay, so it is time for us to engage in sentiment analysis sword fighting. Of course it is. So your task for the next bit of this exercise is as follows. Dan Brush Chalkwood, as you've just seen in that intro, wants to become a data scientist, but to do so, he has to defeat the evil ghost pirate LeChalk. But he's going to have to train before he goes up against LeChalk, and he has to train in the art of sentiment analysis sword fighting. So what he's going to do, he's going to roam HSMA Island looking for pirates to battle, and only when he's battled 50 pirates will he be ready to face the ghost pirate LeChalk. Now you are going to use your models that you have just been playing around with to help him. So in your groups, you're going to make any last minute adjustments that you want to make to your models, but then you're going to take your trained model, the one you're going to go forward with, to help Dan Brush. You're going to run the code saswordfighting.py. Now, a couple of things to note about this code. First of all, you don't need to read through and understand the code, and I mean it's fairly straightforward, but it's the logic for the game you're going to play. You're welcome to look at it after the session, but you don't need to do that at the moment. You're just going to run it. The second thing to know, the model that you have chosen needs to be saved in the same directory as the PI file that you're running, the SA sword fighting, and it has to have the name trained SA model .keras. Now, all these things will be true by default, but if you've moved or renamed anything, be aware of that. And I know, as I advised you, a lot of you were renaming. So you can either rename your chosen model as being trained SA model.keras, or you can go into the SA sword fighting code, and you'll see the file path at the top. You can change that file path to whatever you've called your best model, your chosen model that you want to pick. What will happen is then you'll run this code, the SA sword fighting code. Dambrush will then encounter at random 50 pirates, and each pirate that you encounter will give a review of a service that they've had, and they'll tell you whether that was positive or negative. And incidentally, those reviews are randomly drawn from a labeled dataset, which is from Kaggle, and it has 4,000 reviews for different services. So if you want to check out that afterwards, that's the dataset there. So the pirate will basically say, here's the review of the service I had, and they'll tell you whether it was positive or negative, and they will ask you if you want to fight. Now, if you reply yes, and you do that by entering Y and pushing enter in the message box that comes up at the top, if you're using VS Code, then your sentiment analysis model will then attempt to predict the classification of that review. If your model agrees with the pirate, i.e. it gets the correct answer, then you will win the fight and you will gain 1 point. If your model does not agree with the pirate, you will lose the fight, you will lose the fight, you will flee, and you will lose 1 point. And yes, you can have negative points, so be aware of that. You can choose at any point not to fight a pirate, and you do that by entering anything into the box other than Y or the letter R, and I'll come back to R in a moment. You can just hit enter as well, that will do it. That will basically then move you on to the next pirate. You won't gain anything, but you won't lose anything either. So basically what you should do, for each pirate that comes along, they will give you their review. They'll say, I think this is positive or it is positive or negative. And you have to read the review, or skim read it, and decide whether you think your model is going to correctly classify that review or not. If you think it will, then type in Y and you'll fight the pirate. And then hopefully gain a point if you agree, or you'll lose a point if your model does not agree with the pirate. Now, just to flag up an important note here, there is a long-standing bug if you're using VS Code in the interactive window. Sometimes the output does not show up before it asks you for the input. That's obviously quite a problem for this, because it'll ask you, do you want to fight or not, and you haven't yet seen the review. If that happens to you, don't panic. We've built in a safety mechanism. All you need to do is enter R and hit enter, and you'll then encounter another pirate. It'll basically kick it into gear. You won't lose a turn. You won't get any penalty for doing that. It'll just give you another pirate instead. Just be aware when you do that, when it then kicks back into gear, you'll have 2 pirates in a row. Just look at the newest one, the one at the bottom, okay? Because that's the review that you'll be looking at. You'll also probably find that you'll have a smoother experience if you close down the interactive window first, if you've got one open, and then open a new one. You may even find it might be worth closing and reopening VS Code can help, but it's not perfect. I did it with Sammy yesterday and still encountered it. So just be aware, this is a VS Code specific thing. If you're using Colab, then it won't matter. So, after you've had 50 encounters with pirates, each one of them will come along with a pirate name as well. And that's 50 encounters whether you choose to fight them or not. You'll then be given a final score. And you should post your final score in your PSG channel on Slack. You can only play the game once, unless you have some sort of catastrophic technical issue, of course, to submit your score. So you can't go round and try again. You can only play it once properly. Now, to ensure fair play, because it would be fairly easy to cheat on this, and there are going to be some significant points up for grabs in the next bit. So to ensure fair play, because you're all dastardly pirates, one member of each peer support group should go into the next peer support group to act as an impartial pirate observer to make sure everything is being done fairly. So you should go into the next one down in the list. Somebody from Zylog should move to Agnus, the first group, and so on down the list. Just to clarify, we'll leave the RJ Macau group open for this. They won't be taking part in the game, but you are very welcome to still be in that group if you wish, or you can go to your home group. But you don't need to send an observer into RJ Macau, so you can jump over that. So once all the groups have completed their encounters and you've all posted a score in your peer support group channels, the top 3 scores will get 15, 10, and 5 peer support groups, but PSG points. However, more importantly, the group with the highest score will go on to face the Ghost Pirate LeChalk in a final battle. Right, any questions that have come up, Sammy?
Nope, I think we are okay.
Brilliant. Okay, just to what I'm going to do, I'm going to run the code just on the stock model that I've got, just for a couple of encounters, just so you can see how this will work. So if I switch over, here we go. This is the code to say you don't need to run through it. If you do want to change the file name, if you've named your best model something else, change it here before you run it. Okay, but you don't need to change anything else about the code. So if I, sorry, this thing's always in the way. If I run this code now, run it in interactive window, you'll see what will happen, hopefully. There we go. I'm Danvers Chalkwood, I want to be a data scientist. Right, encounter 1. You have encountered Bill Bones. They want to fight. They exclaim. And this is the review, which I'd recommend you just sort of kind of skim over and read this review. This is a genuine review of a service. They will then say what they think about it. So they'll say, and I say, "'Twas a negative experience. Shall we fight?" I then have to make a decision. Oops, let me just move that out of the way. Whether to fight that pirate or not. If I decide to fight, my model needs to agree that it is negative. So I'm going to try and fight. I'm going to type in Y. Let's see what happens. I clash swords. I also say it was negative. Great. I've won the fight. Fantastic. I've now got 1 point. And then the next pirate comes along. Maximus Dark Skull. They want to fight. And so on and so on. I'll just demonstrate, just in case you do get that bug. Obviously, I haven't encountered the bug here. If I wanted to, if you do get that bug, if you type in R and hit enter, it'll just give you find another pirate, and you don't get any penalty for that. Okay. But if I don't want to fight, I can just type, I can just hit enter without typing anything in, and I'll make my excuses and leave. I don't gain anything. I don't lose anything. And I notice the bug has now appeared. So it's come up with the points. It's asked me for the whether I want to fight. It hasn't come up with the next review. At this point, I would type R, and it'll kick into gear. What you'll see here is that for encounter 3, I've now got 2 reviews. Ignore the first one. Just look at the second one. That's the one we're answering. Okay, hopefully that's all clear. So you've got, well, we're going to see, you've got until around 20 past. As soon as you're done and you've played the game, you need to post in the scores. So if everybody is done and posted the scores, I'll bring you all back. Okay, but go off now. You've got a tiny bit of time if you want to make any final last-minute adjustments to your model. But you then need to pick the model you're going to fight with and then go for it. Okay, so I'm going to open up the breakout rooms. Go and fight the pirates. Let's see what happens. Okay, everyone, welcome back. So it appears everybody has submitted a score now. That was very entertaining to watch. Watch your sort of panic trying to do this. So I can now announce the top scores. a lot of the scores fairly similar, actually around the middle. One a bit lower, most around the middle, but there were 3 top places. So in third place, I can announce that it was Arm with 31 points. Well done. You've got 5 PSG points for that. In second place was Agnes with 32 points. So well done, Agnes. 10 PSG points. But romping to victory is Sid with 35 points. So well done to you, Sid. Now, of course, you get 15 PSG points, but it doesn't end there, because now we're going to go on to the very, very final battle where everything could change. So let's bring up the screen, because, of course, all this training has been to try and get our training ready for the battle with LeChalk. Oh, sorry. Okay, so here is LeChalk's battle. So the winning team, so that was Sid, are now going to face LeChalk in a deadly battle, and could potentially win, on top of their 15 PSG points, an additional 100 PSG points. I do emphasise the word could here, and I'll explain why. So, LeChalk, having heard of plans to fight him, as you'll have seen in the intro video, took the ultimate protection against sentiment analysis sword fighting, that is, the power of sarcasm. So he has assembled 10 sarcastic reviews, one from each PSG. You'll recall you all wrote in your groups some sarcastic reviews. So the winning PSG, Sid, you are now going to battle LeChalk using your model, and you will fight against LeChalk. He will fight back with the 9 sarcastic reviews not from your group. So all of the other sarcastic reviews not from Sid, you are going to have to fight against them. And for every review that your model will go up against, it has to try and correctly identify the review as negative and cut through the sarcasm. And for every review that you correctly identify as negative via your model, you'll win some PSG points. With the more ones that you correctly identify as negative, gets you more points. So should you cut through all 9 sarcastic reviews, you will get a bonus of 100 PSG points. That goes down to 50 for 8, 40 for 7, 35 for 6, etc. This is on top of the 15 that you've got. That's safe. You've got that in the bank, but there are additional points up for grabs here. So I'm going to ask the winning group, Sid, what you now need to do is to post your winning model, your Keras model, your .keras file. Can you please post that in the Sid PSG channel? So just drag and drop it into the message box, hit enter. I'm then going to download the file. I will move it into my directory. I will rename it the winning model, and I am going to do battle for you with the code that I will share with you after. Basically, this will read in each of the sarcastic reviews, and it will do battle, and it will tell you how many you managed to cut through. And note down there, I must move out to the Opera directory, not the Git folder. Thank you, Dan. Yes, I'm glad you said that. So let me skip over to Slack. Let's see, Sid. Sid, here we go. So this is your trained model. So let me download that. Let me minimize this so I can actually see what I'm doing. And then cut. And then place this in this one. Yes, I can replace that. I will delete the winning. This is just my base model for testing. So I'm going to rename your model. Oh no, if I can spell. Winning model. Okay, so this is the code. I'll bring up the code now for the final battle with LeChalk. I'm still in. Let me just close that down a bit quicker, and I'll reopen VS Code. Okay, so the final battle with the chalk. Close that down. So it's going to read in all the reviews except for Sid. So I'm going to tell it to get rid of Sid's. You'll see Sid is review number 8. Let's see how you get on. Let's see if you manage to get any points at all, and if so, how many you do. So we want to ignore group 8. Let's see what happens. Off we go. So it appears that we had just one negative prediction out of all the reviews. So your model predicted Agnes to be positive. The review about Discworld, Antics review of A Bank Holiday on a Hill predicted to be positive. Arm, Keeping Up the Kardashians predicted to be positive. Denise was predicted to be positive. Motorola was the one you managed to cut through. About Cornwall, funnily enough, your sarcastic review of Cornwall, your model just managed to classify that as a negative. Paula's review of Great Western Hospital, positive. Pokey's review, positive. TIA, positive. And Zilog, positive. Nonetheless, you did get 5 bonus PSG points there. So well done. You managed to get 1. You could have got 0. So you did manage to just eke one out with your model. I will also say as well, out of interest, I did this using the stock model that came out of the box, because I already had access. So with just the numbers we plugged in at the start, yesterday with your reviews, because I had your sarcastic reviews to see what would happen, and depending on which review you ignored, you were getting between 3 and 4 correctly identified as negative. So unfortunately, your winning model has been excellent for fighting those pirates, but LeChalk has unfortunately largely defeated you. But you did manage to scrape an extra 5 points there. So well done to Sid. Still a victory. So 20 points to Sid. Fantastic outcome. And that's it. So well done to everyone. I hope you've enjoyed this afternoon's session. A little bit different. You'll probably have noticed, as I sat in with TIA earlier, and it was pointed out, some of these reviews as you were going through, let's remind ourselves, you trained your model on a movie review dataset. Maybe that is not the best thing for reviews of services. Maybe it is, but it may be picking up things that were not quite so relevant, or not picking up things that may be more relevant. So thinking about how you train your data, your models based on the kind of models that you the kind of data you feed into it as well is hugely important. But hopefully it's given you a bit of an overview of text classification. Sentiment analysis is one example of that. Some of you may go on to do some of that for your projects, but you may have ideas for other ways in which you can classify text. You can use exactly the same approach to do so, and also multi-level or multi-class classifications as well. If you've got more than 2 classifications, you can do that too. So lots to think about for your projects. So next week, we finish off the natural language processing module in a very different way. We've got a full day hackathon next week. And I will say next week, potentially, there could be, one group could technically walk away with over 200 points. But there will certainly be at least over 200 points available to everyone. Whether how that's distributed across the groups, you will have to see, and it will be very much down to you. So there's going to be lots of interesting stuff to do next week, using everything you've learned both today and last week to try out some of this stuff on some real data sets. Okay, thanks everyone, and I look forward to seeing you all next week for the hackathon. Thanks everyone. Bye-bye.